Welcome to the next episode of the Staying Money podcast. You guys all know me from our regular interviews, and today Juan couldn't make it, so we have Jocylene, who's going to help us interview today. Go ahead and introduce yourself, Jocylene.
Hi, everyone. I'm Jocylene, like Krystal just said. You guys are used to seeing me in Staying Money news, but thank you for having me as your co-host this time.
All right. Today we have Nathaniel Bowling, who has a bachelor's in mechanical engineering, and he was recently made a team lead at Cummins. So congratulations, Nathaniel.
Thank you.
And Cummins this is the wiki description. It's an American multinational corporation that designs, manufactures, and distributes engines, filtration, and power generation products. So Nathaniel's job involves electronic hardware integration, right? So
correct, yeah.
Is there anything else you want to tell us about yourself to introduce yourself, Nathaniel?
Sure. Yeah. So it's pretty cool. I grew up in Indiana, which is where Cummins actually started from. So in Columbus was kind of the home base there for a while. And we just celebrated 100 years at the company. So the company's been around for 100 years. It's pretty awesome. So I went through high school and college and everything. And then you get to the end and you're like, okay, I really need to look for a job, right? And it's like, well, Cummins is right in my backyard, right? It's engineer, go do engine stuff, right? How cool is that? So
yeah,
that's where I landed.
Yeah, they're known for like diesel engines the most, right?
Absolutely. Yep. And we've gotten into some pretty cool new stuff as well. With natural gas, we've made natural gas engines for a little while, and then lots of cool new technologies too that we're working on right now. And it's because the industry is changing a little bit, so we're definitely moving with that and working on the next best thing.
All right, so let's start a little bit before you started working professionally. Like during your undergraduate studies, during the time that you were getting your degree, you mentioned that one of the things that you did was interning at machine shops, which I think is pretty cool. I think that it makes for a really good engineer because, when you're machining and actually making the parts, you get a really good like intuitive sense of whether your design is actually something that can be made, right? So tell us a little bit about like how having like a machining background and like also the company that you worked for, like what did you do? How did that background kind of help you in terms of being a good engineer?
Sure. Yeah, it helped in a couple ways. And the first you've kind of led into here with the machining piece of it. And I grew up, it's kind of cool. I grew up and my dad was a programmer. So, and for really, really complicated type parts, like literal rocket type parts. And so they're, complex machinings, where you're making one or two pieces and it's got to be right. And so he's dealing with the cases where engineers try to design something that's, maybe difficult or impossible to manufacture, right? And then he's got to go back and feed that feedback to them and tell them, hey, I can't do this, or here's what you can do to make it better. So I grew up around that. And then I interned at that same company. So it was really neat getting to see extremely complex geometry, really get to see kind of what's possible, kind of the extremes that you can get into, but then also, getting that background and having people show you, yeah, here's the process. And then later on, when you're actually designing parts, you're starting to think ahead. What is that process that they're going to use? So I don't make their lives difficult, right?
Yeah. What kind of like specific machining did you do? Was it a lot of like lathing, milling? Was it mostly CNC? Like what kind of processes did you do?
So I didn't do the work specifically. It's all kind of divided up, right? Where you got engineers in that specific company that I interned at. You have, engineers who develop the process. You have engineers who actually do the programming, and you have technicians who run the machines. And so I was interning with the engineers who do the processing, but then I had to go out and actually talk to the machinists, and I, talk to the programmers, because my role was to actually estimate the time that it would take to do a machining job. So I had to go out and figure out all the different types of processes, right? The lathes and the 3-axis milling or 5-axis milling, and figure out, okay, what are those machines capable of, and how much time is it going to take for a part to be machined. So I got to see all that. I didn't get to do it directly, but I was definitely around it in that process. And so that the second part where I gained a lot of experience was doing Excel work, and actually doing some Visual Basic work. And so that, when I was, looking at, trying to figure out how to calculate machining times, there was a lot of inputs, right? You take the inputs of, the part and the process that you're using, put those into a calculator, and it, then starts, crunching the numbers. But the calculator I developed used Visual Basic. So you got actual like user forms, and then code behind the user forms and the buttons. And so that then transferred in, to my work that I did for Cummins when I actually started processing data for test cells, because I could actually do more complicated, reports on data than I would have been able to if I hadn't had that experience. So that was the second way. It helped me out a lot.
So just out of curiosity, how do you estimate time for things? Is it like the number of holes, the number of passes on something?
Exactly. Yeah. And it's been over 7 years since I did it. So it's not super fresh, but it's exactly that. It's, starting to take a complex geometry, right? And try to categorize the features, like the surface that you gotta mill, or the volume that you gotta mill down from a casting or a forging. And then, how many holes you got to put in. Do the holes get threaded? Do they get countersunk, counterbored, all that kind of stuff. And then you start looking at the machine capabilities, their speeds and feeds. I think it's kind of the what you hear a lot of times in your machine shops, what they're capable of, and then setup time. Try to estimate, how much you're going to have to put into the setup. All that, yeah, feeds in to the calculation.
I remember we had a lot of fun kind of doing that stuff when we first got into CNC. We used to have kind of other people do that for us, but we wanted to like learn how to do G-code and stuff.
Oh, yeah.
We had so many times where we made we were trying to make a part for the first time, and it just completely like it didn't come out right, or it was like a really bad finish, not accurate measurements and all that stuff. So
yeah, it's amazing. It's super complicated, but the technology and the tools are developing so much that you can make almost anything nowadays with 3-axis and then like 5-axis machines. You can machine just about anything. Or nowadays, if you want to, if you can't fit a cutting tool in there, you just 3D print it, right?
So just my understanding is like a 3-axis machine, right? You got your X and Y and your Z axis, right? What's the difference between a 3-axis and a 5-axis machine?
Let's see if I can remember. You got, yeah, you're traversing axes, 3-axis. Then you got, yep, and then you got, when you add in a couple more axes, you add in on the milling, like the tool itself, you add in a couple rotational axes. Mm-hmm. So your spinning tool is not translating, it can actually rotate. And that's
that kind of thing.
So you can translate, no, if this is like this is the axis of your tool, right? So in 3 axes you can translate all around. But in 5 axes, you can then actually start to rotate the tool and spin it around those axes. It's fancy. Yeah.
Fun.
Some machines, some machines even go farther than that, right? Where the workpiece that you've got and you're holding, you can put it on a turntable. And so now you can actually turn the part that you're working on while you're machining it. And that, that gets really complicated, right? The code, you can imagine the coding for that. But you can use, 3D modeling software and programming software to help you with all that. And you can make a lot of cool stuff.
So for like the Visual Basic work that you did, I bet that there's probably a lot of people who have never used it before. Can you give us a little bit of rundown of like, what kind of things do you use it for? What is it helpful for? Like, why would you use it over something else?
Sure. You use it, I guess, because it's there. It's what's there in Excel, right? So you got, your basic Excel functions, and then, you can work in the spreadsheet, right? And then, but, for whatever reason, Excel actually, they put in the Visual Basic type coding language. And so it's there, so you can use it, but it's not too bad. It's fairly simple, and you can Google it. Basically, that's how I learned it, was Google, like Visual Basic, do XYZ function, and then start browsing, posts and forums on how to do it. The other thing you can do, I don't know if this is new, most people probably know this, but you can actually record your clicks and your operations in Excel, and they call it a macro. But you can go in and you can manually do something in the Excel spreadsheet that you want to maybe make automated, but you don't know the code to automate it. So you go and you do it manually while Excel is recording your actions, and it will convert your actions into the Visual Basic code. So then you go in there and you look at it, and you're like, okay, what did it write to make those actions happen? And then you can start to see, okay, yeah, here's the variables that were put into it. Here's the outputs. And then you can start manipulating it and learning more about it, through your Google searches and write your own code. So it's those two things are pretty powerful. It helps out a lot.
That's what I do as a software engineer every day. You just Google it.
Yeah. Google knows. Google and YouTube. Someone knows. Someone's done it before, right? And if you can find out who that is, you don't have to reinvent anything.
I would like to ask something. For most Cal State LA students, we are used to using MATLAB and Arduino, stuff like that. How would Visual Basics be different from those?
Visual Basic compared to MATLAB, and I think MATLAB can do a lot of this too, but I think Visual Basic's really set up to work well with like user forms and inputs, and actually, creating graphical things. So I may get this wrong. Someone who's more familiar may be able to correct me on this, but I think MATLAB is definitely more powerful and set up to do complex mathematical calculations. It's set up to be really friendly towards complicated math functions. So you got, built-in, commands that'll do what maybe it would take Visual Basic several lines to do, is my understanding of it. So it's very powerful for math. Visual Basic just adds in that user form, friendliness, where you can create, buttons and drop down menus and all that fun stuff.
That's
Cool. Thank you.
So one of the things that you mentioned to us about what you've been up to and kind of like the hobbies that you have, and it's kind of exciting. You said that you have a 4-wheeler. So tell us about that.
Yeah. So when you're in school, right, you're learning, but you're very poor, right? You're not making a lot of money, and then you graduate and you find an engineering job, and then you're making money. So after that, you're like, okay, let's have a little bit more fun, right? Since now I got some money. So I decided to build stuff, and that became a little bit of a money pit for me. But it was fun because it was still engineering kind of like as a hobby. And I even got, more hands-on experience, actually turning wrenches on my four-wheeler, because I completely tore it down from a functioning four-wheeler that was built in 1986, 30 years old, right? It had almost never been rebuilt. I tore the top end of the motor open, and it still had what looked like an original OEM piston. So 30 years that thing had run and never been rebuilt. So tore it down to the frame, powder coated everything, and bought new suspension parts, rebuilt the top end of the motor, painted the motor, polished a bunch of things that I probably didn't have to, but just for the fun of it, right? Just sanded aluminum, sanded all the paint off of aluminum and polished it and made it almost a mirror finish. I could pretty much see my reflection in it, and then took a bunch of pictures of it, and then I wrote it and wrecked it, and it was okay. I kept writing it. And so it's fun. I mean, it's one of those things where engineering, an engineering background makes you better. And you take, at least, a 4-year engineering degree, you learn how to solve problems. And so then when you have a little bit of expendable cash, right, and you want to pick up a hobby, you still have that capability, right? You know how to solve problems. And so you apply the funds that you have and solve problems for fun.
So in Baja, we we're not allowed to touch the engine. So that always makes me a little bit nervous. Like even like in my car or whatever, like I probably won't touch it. I'll probably have somebody else help me out with that. But like what's the benefit of rebuilding the engine? Like what's the biggest thing that you're going through? Because my understanding is like you're taking it apart and you're putting it back together. So like what's usually like the goal in an engine rebuild?
Yeah, there's multiple things. For me, it wasn't too complicated. It was mostly just rebuild it for fun, and because I didn't really know what condition it was in, and so I took what they call the top end off, and for 2 strokes, which is what this one was, it's really, really simple. And I'm assuming that probably your engines are 4 strokes.
I think so.
Brennan?
Yeah, I want to say so.
Okay.
Lawnmower
Yeah.
engine.
Yeah. Those, I'm pretty sure those are 4 strokes. 4 strokes get a lot more complicated because you've got complicated timing mechanisms that are opening and closing the valves to complete the 4-stroke cycle. With the 2-stroke cycle, the flow dynamics in the engine are a bit complicated, and I don't really understand it. But mechanically, it's really simple because there's no timing to open the valves. The piston in the engine actually becomes the valve that completes the intake and the exhaust strokes. So it was really easy for me. I thought, yeah, let's tear it open and check it out. And for me, like I needed to do that just because it was a 30-year-old engine, and you have the sealing rings that go around the piston. Those eventually wear out. Stuff like that wears out, and so if you have the opportunity right on something like that and it's simple enough, you might as well take that apart so you get more life out of it. Now a lot of people, when they take stuff apart, they'll try to make it even higher performance, right? So they'll take an engine, and if you have enough material in the cylinder, you can bore it out, which increases your engine displacement. So more displacement, more power, right? And you just you got more power than the other guy, right? And so the other things like you can polishing ports and optimizing airflow and changing the carburetor, jetting, stuff like that. There's all kinds of stuff you can get into with motors like that, and that's what people do.
For like a super basic rebuild, are you usually looking to just like replace rubber parts that have gotten really like crusty? And
yeah, sometimes.
yes.
Yeah. So the piston, I replaced the piston on mine, replaced the wrist pin. I think the wrist pin or the wrist pin bearing, I can't remember. Where that connects the piston to the connecting rod. And then, yeah, I replaced, gaskets, that were old, and replaced the carburetor because I thought I might be able to get a little bit more power out of the carburetor, change the exhaust on it, trying to change the airflow a little bit and stuff like that.
All right. So like what was it maybe like the hardest part about taking it apart and then putting it back together again?
I remember one really annoying hard part, because again, like this thing most of this hadn't been taken apart, I don't think, like since it was built. So there's a part on the four-wheeler called the swing arm, which is the arm that connects the frame to the rear axle. It's kind of interesting. It's like a solid rear axle. So I see, like on your picture there, it looks like everything there is independent suspension, right? So the front suspension on my four-wheeler is set up very similar to that, but the rear suspension is just basically one shock absorber with a linkage connected to the swing arm, like a dirt bike, basically. But then at the end of the swing arm, you got the axle that connects to both tires.
Okay. It's like one bar that goes like all the way across, right? Wheel to wheel.
Yeah. Yep.
And then like the suspension just straight down kind of thing. Pictures that you sent us.
There's a linkage. I'm assuming it's probably like ultimately it's probably like a 4-bar linkage setup, but I can't remember exactly. But yeah, you got the basic motion is just is like a 4-bar linkage, where you got the swing arm as one of the links in a 4-bar linkage, and then your shock absorber is like that sliding joint in the linkage, and then your frame is the ground reference. So then, but yeah, that linkage, or the swing arm has a massive bolt, probably the biggest bolt on the whole thing, and that hadn't been apart for like 30 years, so it was just like rusted into everything. And so I was, just like hammering on it, like spraying WD-40 and PB Blaster on it, hitting it with like a torch, trying to heat it up, beating on it again. I tried to make my own little slide hammer to like yank it out. And eventually I just ended up cutting it. I cut right between like the frame and like cut the bolt in half and pulled the swing arm out and just like beat the bearings out of it. And so that was the absolute like hardest part of it, was just physically getting that thing apart.
Do you remember what size it was, or like what size tool you would need for it? You remember?
And it's probably at least an M12, maybe an M14 screw. Yeah, it was. I can't remember. I can't picture the size in my head, but it was big. Yeah, and it was probably 6 inches long or more, going all the way through the frame.
Oh.
Yeah.
My goodness. Yeah,
so that was the physically the hardest part. I'm trying to think if there's anything else. I can't remember. Like, I think maybe just organizing the project, because I'd never done it before, right? So you bring those engineering skills, right? You kind of learn in your classes, right, how to manage projects a little bit. So you're trying to kind of do that same thing, right? Okay, what do I want? How much is it going to cost? Probably more than I think originally. What all am I going to do to this thing? Am I going to replace everything? Am I going to recondition parts? And then, doing the work yourself. It's a little miniature project that you got to manage. But the thing is, when you haven't done it before, you don't know what processes you're going to use, which is kind of that really valuable experience that you gain when you do things hands-on. And, the more projects you take, the more you learn. So you get that experience to where the next time you do something like that, the process. And so that's, I think, the value in doing, projects like that is just learning new processes, so that in the future, you're able to make design and judgment calls already knowing what you're going to have to do in the future. And it gives you a lot of advantage when you're planning.
think going into it is probably just like you're thinking, oh, I'm just gonna make everything shiny.
Yeah. Yeah.
And then you learn that there's like way more
Yeah.
involved in it than just polish.
Put some parts. Yeah. Parts don't fit. Like you buy aftermarket parts and like a lot of times they never fit exactly the way you thought. And so you gotta come up with something new, right? You gotta figure out how to make them fit or adjust.
You make Jocelyn take apart the steering for the Baja car. You take it apart and put it back together.
I did
Yeah.
that. I took it apart and I put it back together, but for some reason I had swapped some parts and the parts were done differently for both sides. And then the next day the captain came at me and was like, yo, why can't I like move this at all? I can't move it was yeah, I had to take it apart again because of that. But
It happens. A lot of those things look super identical. It's hard to tell like which one's the right side, which is the left side. I think like even in our car, like I think we've made the move kind of to make them more symmetric on each side. But I don't know. I think it still matters a little bit.
That's really cool though, because like what you're doing is literally learning what we do at Cummins, which is you call it servicing, right? So you're going to build a product, right? And as much as you like to think, all right, it's going to be perfect and you're never going to have to work on it or repair it, something will break. Like eventually, like if you run it for 30 years, something's going to wear out. And if you're thinking ahead in your design towards the poor guy who has to take it apart, right? And then like with the steering stuff, right? You got to take it apart, and then if it's not obvious how it fits back together, right? If things aren't symmetrical to where they fit in the same area, or if they're not like perfectly, or they're not asymmetrical to where they can only fit one way, right? Then the person who's servicing your product gets really frustrated, and it costs time and money to do that. So you guys are gaining experience there that applies when you get into designing products.
okay, so now that we're back on the topic of Cummins, I was wondering if you said that you did some test working on diesel engines. What goes into the test process of that?
Yeah, that's really interesting. So there's a lot that goes into it. And I started that role as my first role in Cummins, doing the test engineer role. And it's really neat because it's a really challenging role, and you're working with assets that are extremely valuable a lot of times, right? Because when you're testing prototype engines, right? And they only build so many of these things, and versus like an engine that's in production, they're extremely valuable, and there's many hundreds and thousands of ways that you can break them. And so you take this this fresh engineer out of college, right, and you give him an extremely valuable asset, but they're really good at putting you under mentors, right, and making sure that you're supporting before you're actually owning tests. So it's amazing because you get to see the engine running, and you get to see all the ways that it can break, and you get to see all the different data points that you can collect on it, process the data, interface with the engineers who designed it, interface with the engineers who are validating specific parts on the engine. It was really awesome experience to be able to see that whole system working together. So when you're setting up, the tests, you start, from a test plan, that usually there's someone, requesting a test. There's a group of engineers who want a specific test done. And so you develop the test plan, you kind of translate their requirements, develop the test plan document, plan out the timing when you're going to get the engine, plan out if there's any changes you got to make to the engine, because sometimes the engine will come kind of in a maybe a semi-production state, and then there's a bunch of instrumentation you want to add to it. So you want to add a bunch of thermocouples and pressure transducers to get a bunch of data at different places. So you got to plan out, instrumentation work, plan out when you're going to go into the test cell, coordinate with the team that actually runs all the test cells and make sure they're aware of what you need, because there's a ton of equipment, right? And then you install the engine in the test cell. The test cells are kind of generic. They're set up to, take multiple sizes of engines and configurations. So you got to figure out, how we're going to mount the engine. There's different mounts that you select to mount the engine, hook up all the instrumentation, connect your coolant supplies and make sure you've got oil in the engine. That's pretty embarrassing if you forget to put oil in the engine. So don't do that. Make sure there's oil in the engine, make sure if there's, periodic maintenance that needs to be done, you get that scheduled, make sure the technician who's doing that is aware, run the engine, set up your data loggers, set up your limits, because they're, if you're testing your engine and you're getting close to certain values on certain, temperatures and pressures, you want to stop the test, right? You don't want to keep running your engine if something's breaking. And a lot of times you can do that. You have a lot of advantages in a test cell where you can get extra data that you don't get when the engine's in a truck. And so you can stop the engine if it's about to break. Then you try to set up your limits, and then you run the test and collect the data and help process it. And at the end, you pull the engine out, and sometimes you tear it down and inspect it, take the whole thing apart, check every part, make sure nothing, broke or was about to break. Provide all that feedback and that data to the engineers, and sometimes rebuild the engine and run it again, use it for something else. But that's kind of high level. The process is really cool. There's a lot. Every single one of those things is detailed, but it's great.
So when you say that something's going to break, right? Because I feel like a lot of testing is, like you said, is when you're trying to see if something will break or if it gets too hot. But like, what exactly would be breaking in the engine?
So at kind of a high level, like if the engine itself, right, if it's doing its function, right, if it's putting out the required amount of power, it's kind of not broken at a whole system level, right? So if the engine's working, it's not broken, but something could break on the engine that if you don't catch it down the road, it escalates and it causes progressive damage, and something will break. So obviously, right, if you forget to put oil in the engine, right, and you run the engine and you lock it up, then you definitely broke the engine, right? Your pistons are seized to the cylinders, or worse than that, if you're running at full power, right, and something locks up, that energy has to go somewhere, right? It'll literally explode a piston through the block.
Did you ever see that happen?
I have not seen it happen. I have seen the aftermath, and it's kind of painful. If it's interesting, it's really interesting to see if it's not your test that blew up. If it's someone else's test, it's really interesting. We can go check it out and see what happened, right? If it's your test, you're like, oh, I don't even want to go look at it, right? I want to hide. But yeah, so there's definitely catastrophic failures that can happen from either sometimes you literally make a mistake, or sometimes you find out limits that weren't set properly, right? And you find out as a design flaw. And if you're going to break something, you want to break it before you put it into production, right? So you want to abuse it, and literally we do what we call abuse tests. We abuse the engine to try and make sure that if it's going to break, it's going to break here in a controlled situation, and not on the customer. But then there's tons of other failures, right? The engine might have still been running fine when you in the test. Then you tear it down, and you can find signs of pending failures. So you can look at all the components, right? You can look for oil leaks, coolant leaks. You can look for scuffing or galling on different components. You can look for cavitation effects where you start to erode material. And then you can make assessments, and you can figure out, okay, this component was wearing in such a way that it, you know, it could have failed, and you know, in some future way, right? And then you start making engineering assessments, right? Was I wearing out my engine in a bad way? Was this normal? Would it have likely resulted in a failure at some point? That kind of thing. So even stuff that's not really broken, sometimes you call it a failure, and you go back and you try to redesign it and figure out what was going on.
Can you give us a little bit more background on what abuse testing is?
Let's see. I probably can't tell you some of like the specific tests that we run, because some of that like is we develop our test standards, right? And we're good at it, right? Because we make engines. So I can't probably tell you exactly how we test them. But I mean, imagine, yeah, the ways that an engine can fail, and you know, the temperatures and pressures, and you know, fueling. If you take some of those parameters to the extreme, what happens to the engine, right? So you do things, you know, that maybe are normal, but do them excessively, you know, to the engine to accelerate wear or accelerate, you know, damage, and then try to assess how the engine performs. I don't know if that was helpful or not, but yeah.
Basically like pushing it to its hardest limits, right? And
Yep.
see what happens, kind of thing. Where like maybe the conditions are like more extreme than what they would be if it was just driving in a car.
Yep.
So like speaking of engines, so you guys do like a lot of diesel engine. And so, you know, like my perception before realizing that you worked for Cummins was that diesel engines were like really old and really outdated and that kind of thing. But you know, I started looking into it and was learning that there's been so many advancements that I think probably a lot of people have a big misconception about how they perform, what they do, like their environmental, the way that they affect the environment, right? So
Sure.
let's kind of get into a conversation about like myth busting, what people's perception of them are, and like how they actually perform. So one of the things that I learned was that one of the things they said is that highway miles, people who drive like a lot on the highway or long distances, they prefer diesel because they're more efficient compared to driving in the city.
Yeah, the fundamental difference, you know, between a gasoline engine and a diesel engine, right, is their fuel type and their ignition method. So like with a gasoline engine, right, you got a spark plug that ignites a fuel air mixture that creates, you know, the chemical reaction that generates energy to drive a piston, right, to drive the connecting rod into the crankshaft. You know, crankshaft rotates, get rotational power, right? So you have the gasoline version of that, where, you know, a spark ignites that chemical reaction. With a diesel, you have basically you have only the compression generating heat in the cylinder that creates the combustion. So they're fundamentally the same four strokes, the two engines. You got intake, compression, power, and exhaust. They all do the same one, but diesels, they have a whole lot higher compression because they use that compression to generate heat when you compress the air that then ignites the fuel. So then, yeah, that's the fundamental difference. I think, yeah, a lot of times that you'll find that diesels, I think just by virtue of that combustion process, they get better gas mileage. But it's pretty interesting. Two different fuel types, right? I think ultimately, and I haven't really studied the chemistry of it, but I think, yeah, they're both, you know, oil, petroleum-based fuels, right? One, I think the gasoline is actually more refined. It's kind of interesting. It's weird. The gasoline is more refined than the diesel fuel. But you can get more power and you can get, better gas mileage out of those diesels. It's also, like you said, there's kind of the conception of, the diesel process being like a dirty combustion. But really, yeah, there's a lot of ways that you can optimize it. And that's, I think, part of why, Cummins is so successful, is that we figure out how to optimize it. And we're really good at figuring out how the combustion works, and, how we control our engines and all that good stuff.
Yeah, so this article that I that I was reading was basically saying that like diesel is not as dirty as I think like a lot of people think it is, that there's been so many advancements in kind of making it as green an option as a regular combustion engine. So
Yeah.
kind of going in that direction, if this is a viable source, like what kind of customer does Cummins have? Who do they sell diesel engines to? I mean, I know like in the US, they were saying there's only maybe like a handful of vehicles that use diesel engines. So like, why do you think, and this could be totally personal opinion, but like, why do you think not as many people use diesel engines in their cars? And like, who's actually buying them from Cummins?
I think probably some of it's cost, because a lot of times diesels are developed for more industrial long life applications, and sometimes you don't need that in a car, right? You can make diesel engines. I mean, you could make any engine, but diesel engines a lot of times are specifically designed to last hundreds of thousands of miles, sometimes 500,000 million miles. You can get that out of a diesel engine. Then you rebuild it and get another million out of it, right? So they're built really really well. I think maybe some of that is maybe just cost prohibitive for something like a car, but you see like all the heavy duty trucks, right, on the highways, they use them, because of the the reliability and the power you get from them. Yeah, I don't know. Sorry, did that answer your question? I kind of lost track of the question.
Yeah, for sure. But one of the other questions was like, who's like Cummins' main customer?
Yeah, so I mean, ultimately the engine, right, at the end of the day, all it's doing is delivering, rotational power. So, which is really useful. So, rotational power is kind of generic. You can hook it up to anything, right? You can hook it up to a transmission to turn wheels. You can hook it up to a generator to turn, a genset that creates power. So you'll see engines. It's pretty amazing. Cummins started out like with a single cylinder engine, right? Like one cylinder working, and now we've got engines that are like V16s putting out 5,000 horsepower, like I think like, I'm trying to remember what I saw on the website, like 17,000 foot-pounds of torque. So you can scale diesel engines, right, all the way from something that, would power almost like a lawnmower, all the way to something that you see in like railway applications, right? You put a massive engine in a railway application and generate electrical energy. So they're just really, really convenient, right? Because you take they fit in a small package, compared to maybe like a steam engine or something, right? You can store them in a small package. You can store the fuel in a small package, and that's their appeal, is that then you use that energy to do whatever you need to do. You can put it in a truck, in a boat, in a train, in a generator. Anything. Generators are pretty awesome. I think that I like that application, because you can use them and you can really optimize an engine to, if you're running a generator at kind of a single speed, right? You're not doing a lot of transient type operation. You can really tune that engine to perform its best at that specific speed where you're running the genset, and it can get really efficient, really, really clean. And then you can provide, backup emergency power to hospitals and, critical infrastructure, stuff like that.
What's the smallest diesel engine you've ever seen?
I think I've seen a diesel engine in a lawnmower, but I don't know how big it was. It was like one of those zero turn mowers. So it was probably like 1 liter. It's probably like 1 liter diesel engine, something like that.
What's the biggest one?
In pictures, I know I've seen a 95 liter that Cummins.
Oh my, like roughly size wise, like what's like an object that you could compare that size to? Like, is it as tall as you? Or
let's see here.
Justin?
Yeah, probably. I mean, you can pretty much lay down in the oil pan. Like it's about that big. Like you could
lay down in the oil pan. That's crazy. Yeah. Oh my God, just take a bath right in there.
So that yeah, kind of an approximate size comparison. But yeah, they get pretty big. I think there's even bigger engines out there, like than what we make. At some point it becomes really specialized and kind of a custom type engine versus like a mass production assembly line produced engine.
Let's kind of go into a little bit what you do now. So you said that you do electronic hardware integration. So what does that mean?
Yeah, it's pretty interesting because you hear the electronic part, but I'm actually not an electrical engineer. So I'm mechanical. I got my bachelor's there. But there's a lot of mechanical interaction with electronics, right? And it's pretty amazing, how electrical things have become. And it's tricky because electronics sometimes tend to be maybe some of the more fragile type components, right? On an engine, right? Because you're going from like metallic components to now like sometimes copper wire, rubberized components, or plastic components, stuff like that. Things that aren't quite as durable, but there are ways to make them durable. And it's really useful. And so you have the electrical engineering piece of it, but then all of that ends up ultimately being kind of a mechanical system, right? Even though the wires and the connectors themselves are kind of mechanical in nature. So mechanical engineers can definitely do that. So what I do is literally kind of in that title, integrate. So I take all the different devices and I help coordinate between like the components themselves and where they mount on the engine, and help make sure that they're mounted correctly, right? Because sometimes you got orientation requirements for sensors. You gotta think about the different ways that electronics can break, right? Through heat, or through vibration, or through water intrusion causing shorts or open circuits, all that kind of stuff. So you integrate these electronic components in a mechanical way, and physically package them on the engine. And kind of the direct part that I typically end up working on is the wiring harness, because it touches so many parts on the engine. And so that's typically the component that I actually have to deliver, along with making sure that I'm appropriately packaging the sensors and the devices themselves. So that's a quick overview, but yeah, there's definitely more we can get into.
What would you say is the biggest challenge in trying to set up a good system?
The biggest one. There's a lot of challenges. I don't see. Let me think if I can think of the biggest one. That's tough, because you have to design it to where it doesn't break, but you also have to design it to where you can assemble it and manufacture it. You also have to design it to where it's serviceable. There's a lot of things that are equally challenging. I don't know. The literal designing for all of that probably is the biggest chunk of my time. Like, just considering all those factors and literally designing designing the layout, taking all that into consideration. I don't know if that's a good answer or not. I'm trying to think if there's anything else more challenging or specific.
Yeah, I remember that we had like a lot of struggles with that during competition. Some of the longest times we've had in Baja was because our electrical stuff didn't work. And I feel like in the beginning it was like always an afterthought where we're like, oh man, like this thing isn't waterproof. And then we're going in like 5 feet deep of like,
Yeah.
maybe not 5, but definitely like the level of like the driver's like elbow, right? Like it's getting in the cabin.
Wow.
The driver's completely soaked. So there's like mud and water everywhere. And even the people, like the volunteers and stuff, like they're told to just hose stuff down sometimes. So like intentionally make
Yep.
muddy, right? And like we went through this whole process of figuring out like what kind of connectors we should use because they kept like tearing. I don't know how it happened. I think it's just like a really rough environment, there's like rocks flinging around and stuff. So we
Yeah.
have like wires broken or like pulled out of the connectors. And like one of the requirements that they have is like your brake light has to work. Like there's no exceptions to that. And like sensors and like extra stuff that you're kind of using for data acquisition, there's not as many, but then it's like, oh man, like you get one shot at competition until next year. So if you really want to collect data and your system fails, it's like, well, guess we gotta wait until next year, right?
That's pretty wild.
Yeah, so I can imagine like putting it in an actual truck that drives around every single day, not just like during competition. There's probably like a lot of that goes into it. And I don't know, like, have you ever experienced that something had like some kind of like catastrophic like fail or break or anything and like a short circuit in your electrical system?
Yeah, I mean, I think a lot of what you just mentioned, are the same fail modes that we look at, right? Because if you think about your product, think about the North American continent and the different extremes you can get into on that, right? You can go from sub-zero temperatures.
Oh, I forgot about that. The weather.
Yeah. All the way up to, if you go driving out west in Death Valley, right, you can see extreme high temperatures. So yeah, definitely there's tons of experience and lessons learned that we're leveraging when we design to make things not break and to protect them from the exact thing that you just mentioned, right? Mud, water, debris, heat, someone just grabbing a hold and yanking the wires out of the back of the connector, right? There's ways to protect that, and that's the kind of design stuff that you got to do.
You mentioned that you are a mechanical engineer. How
Mhm.
how did that move from mechanical engineer to electronic integration happen?
Yeah, so there was a transition point where the role with the test engineering work was kind of a specific role that you do for when I did it was a year and a half, and then you're expected to kind of to move into other teams and do other types of work, engineering work. So I did get into a bit of modeling when I was in school, and I thought, I like design. I knew one of the guys in design. I was like, I'd like to try it. And so there was then kind of another training phase where you kind of doing general stuff, learning how to do design. And then you eventually start to pick up like more legitimate projects, right? That you can support. And it I don't know, it just kind of happened that like one of the first main projects I picked up was electronic type work. And I don't know, I liked it. I kept it, and it's neat. It's a little bit, I don't know, it's a little bit awkward, I guess, for a mechanical engineer, but it works. The stuff I do, I can definitely do with a mechanical background, and it's fun because I mean it's a component, like you said, that sometimes it gets some afterthought. You don't think ahead as much towards your electronics, and yeah, that's something that as I've gained more experience, it's kind of fun to anticipate that and to try to help convert the mindset to take kind of like the part that some people don't think about and make it a little bit more prominent and think ahead and design ahead for that. And, it's one of the parts that in a way it's kind of weird. It's kind of like an ugly part, like the wiring harness and sometimes the electronics. They're not like the coolest parts on the engine, but they're very visible. And so it's really rewarding when you can take a part that's maybe not as like, I don't know, aesthetic, and then make it into an organized, streamlined, design that actually is it complements the engine, it fits well, it doesn't break, it's really satisfying. I like it.
Yeah, it definitely seems like a lot of fun. I feel like it's definitely one of the more like people put it to the side, but it can really kind of make or break. I mean, like if you can't supply power to your car, like it doesn't matter how great your engine or your suspension or your body or your chassis is, right? Like if you don't have,
yeah,
you don't have, you don't have an electrical harness, you don't have a car.
Yeah. Think about like the analogy I love to make is like the human body, like because you have like your wiring harness and your wires in your engine, and you have your nervous system and your spinal cord, right, in your back, right, connecting. Like your brain is like your computer on your engine, and then like your hands are all the things, little motors and stuff that actuate things, and then you got your sensors, right, your smell, taste, touch, hearing, whatever, right, all that gets connected. And if you pinch a nerve, right, or if you cut your nerves, right, your body doesn't work anymore. And if you cut a wire on your engine or on your vehicle, something's going to stop working because that was, it was connecting something, right? It's a neat analogy I like to use sometimes.
Yeah, definitely. And I do see that it's kind of like a really hard thing to do because like you said, right, not everything usually, like the connections that the wires have, they're not usually like nicely packaged, right? Like there is a lot of consideration of like, this thing is over there, this thing is way over here, how are we going to run a line across this whole car?
Yeah.
And
yeah, that's it.
Yeah,
that's the challenge.
So one of the things that you mentioned that was kind of like a small thing, but I had a lot of curiosity about, was that you mentioned that there's a union at Cummins for mechanical engineers.
Let's see. So there's a couple unions. It's kind of it's interesting. Let's see. You got the goodness, I think it's the DWU, Diesel Workers Union, that do kind of like more like the specific assembly line production of engines. And then you've got like an office union, kind of a more I don't know, I'm trying to think of the right words. It's a union that kind of bridges the gap between like the engineering and sometimes the testing or the drafting work. Because I mean it's amazing the amount of work that it takes, right, to make an engine, right? You think of all the different processes, and so you got engineers doing their engineer thing, right? And you've got drafters who are in a union, following specific processes to do drafting work and drawings and stuff, and you got other union personnel doing specific technical work. So it's an interesting interface that I'm not in a union. I don't know if that's, I'm trying to think if there's engineers who are there. Sometimes it gets gray where you have engineers generally don't get to do as much hands-on work because typically the union is doing that kind of stuff. And then but sometimes you do have opportunities to do fit checks, and there's specific places where we're allowed to touch parts and play with engines and stuff, right? And then you do have union personnel sometimes who are doing similar functions to what engineers do. So there's some gray area. It works pretty well.
Yeah, I feel like it's kind of like a not really talked about thing, right? I mean, I figured like, oh yeah, you're gonna go to work, but I didn't know that there were any type of like engineering specific unions, or like what specifically they provide besides like what a regular employment union would make. So so our engineers typically not union, but they kind of only have that at Cummins because they work a lot with like manual laborers.
Let me see if I can. I think even Cummins. I mean, Cummins has been kind of that's been my home for the last 7 years. So I haven't worked at any other really large companies. So this is kind of the only union experience I have. So it's kind of all I know. But I think in general, the engineering specific functions of like design and analysis, supplier interaction, developing requirements, developing failure modes and figuring all that stuff out. That's pretty much exempt engineering. But some of the specific tasks of sometimes modeling, sometimes Creo stuff, you would use an office union with someone who's specifically trained just to do the CAD modeling and the drafting and stuff like that. I don't know. Does that?
Yeah, I didn't know that there were kind of like different factions in the type of like people in like a larger organization, right? Like,
yeah, there's a lot of people. It's amazing how even just engineering, like how many teams there are, and because it's how complex an engine is. Every single part, right? You can break the whole complex engine down into all of its subsystems, and those are complex, and you break the subsystems into the components, and you can keep diving deeper and deeper, right? And everything you can get really complex down to the component level. And depending on the project, depending on what you're changing or what you're trying to do, there's just multiple levels of complexity. It takes a lot of working hours and head count and different people, different specialties, different mindsets, different ways of thinking. It takes everybody. And a lot of times you won't. I'm trying to think if you could hardly find anyone who understands the whole engine. It's become it's so complex. I think there probably are some, right? There's some people who've been there for 30 years and they've seen it all develop, and you need those people. Like you definitely need that experience. But then you got different engineers working on their different projects, and it takes a team.
All right, so we just went through all of those questions. The last one, where do you see yourself in the future?
In the future, I think I see myself, I love designing and I love building. It's kind of funny because I know engineers, we typically aren't with union interaction. We don't get to be as hands-on, which I think is maybe sometimes why I take on different projects. Like building the four-wheeler, building stuff around the house, because I love the hands-on. I love the whole process of designing and building. So I see myself doing both of those things probably for the rest of my life in some capacity. Just I enjoy it. I love building things and designing things. Now I'm sure it'll evolve a little bit. I just started doing the team lead role, which is neat because I get to have managing experience, but I'm actually still getting to do design work. So I'm getting to kind of do a little bit of both. It's really neat. And then, as I progress, I'm sure I'll try out, different things, different kinds of design, different types of, maybe some more managing, continue to try that out. But I'll always be a designer at heart.
if you want some more building projects, you can always stop by at the the Baja lab. I think the school is in talks about like when would be a great time to like actually have people come back on campus and not be completely virtual anymore. So
yeah, it's tough.
Transition right now, I think, like figuring out how they're going to go about that. But I mean, probably in a year, I would guess that they are back completely on campus.
Where's the school located again?
It's Cal State LA, so it's pretty much like, what is it? I don't even think it's 20 minutes from downtown.
Which city though? I missed it, I think.
It's like East Los Angeles.
Okay.
California.
I'm bad with directions. Where is that with respect to San Diego? Because I've been to San Diego.
It's north of San Diego,
Okay.
like 2 hours north of San Diego. And then
Okay.
downtown LA is like the center. And then it's like a little bit northeast of downtown, I want to say, I think. Or is it
Yeah.
north? I don't know.
Northeast.
It's north.
Yeah, because I've been through Vegas. I've been in where was it? Been up to Zion National Park, in been through Utah and different places there. It's amazing, the terrain that's out west. So yeah, it's really cool that you guys get to drive off-road vehicles and compete and all that stuff. Is it just out west, or where all are there teams in the east?
They're international teams. They have some from Mexico, they have some from China, some from Canada, India, you name it. Most of the competition though is US. I would say like a big majority of the teams are just, for traveling reasons, like the practicality of it. But yeah, I mean, there's definitely teams who travel across the US to compete. That doesn't matter which region. Like for us, 2019, I want to say was it 2019? Yeah, I think 2019 that was our first year competing this car in 2 different regions. So usually we just do the west one because we're already on the west side of the United States. But that time we drove all the way to Rochester, New York. So we went cross country. But there's definitely teams that like they come from, I don't know, they come from Indiana, they come from a lot of them come from honestly everywhere, but I would say like a lot of them come from the Midwest. I think for some reason there's like a lot of Midwest Baja teams.
There's definitely like an off-road community like in the east and different places. Yeah.
I think a lot of it is because the automotive industry is like really, really bumping there.
Yeah. I mean, young people love their dirt bikes and their four-wheelers and their UTVs, and I don't know, if you get to work on engines, right, you never have to like completely grow up, right? You get to
Yeah, definitely. And I mean, like you have Detroit and like the whole like, what is that belt called where they have like all the automotive companies? I forget what it's called. But yeah, it's like a big thing versus like on the West Coast. I would say there's probably more like aerospace related engineering. And I mean, different fields are scattered around, but I would say like El Segundo in near LA is like completely full of like aerospace companies. But yeah, like I would say like the East Coast, or maybe not even the East Coast, like the Indiana area, Detroit and Michigan, they probably have like a really big automotive world there. And probably Florida also has maybe a lot of aerospace. I don't know, because they're in that like area where they can shoot rockets, have them drop into the water and stuff. Yeah. All right. So thank you for joining us. And we hope that you get to build all kinds of really cool, really cool machines and things. And we really appreciate you taking the time to talk about to us about like your kind of really it's an interesting job that you have that not a lot of engineers that we've interviewed have that like that background and that experience. So
awesome.
cool.
Yeah, super glad I could do this. It was fun. It was a new experience for me too. I really enjoyed it.
All right. So one of the things that we offer people is if they would like to plug anything, like if you do or don't want people to contact you, like if you have a LinkedIn or how, like, do you have anywhere that you want people to connect with you?
I don't have anything specific for myself. I would just say, if you're mechanical minded, or if you like science and projects, be an engineer. I think engineering is awesome. I think everybody should be a little bit of an engineer. Like just do a little bit of engineering, something like, I know it's not for everybody, right? But think outside the box, try to think about problem solving, because we do all of that, in our day-to-day lives, right? We all have problems to solve, and solving it in an engineering mindset is valuable to everybody.
All right, so we'll hope to have you on again, and this has been the Staying Muddy podcast. So everybody, thank you for listening, and we'll see you guys next time.
Awesome. Bye, everybody.
Thank you for listening to the Staying Muddy podcast. If you like what we do, join our subreddit, Staying Muddy Podcast, or if you would like to learn more about our team, you can visit our website, Castellet Baja CE, or follow us on social media at Castellet Baja CE. Thanks again for listening.